Chapter 11. The Anatomy of the Infinite. Quote, "The essence of mathematics is its freedom." George Cantor. To measure the plurality of an infinite collection seems a bizarre idea at first, yet even those least conversant with mathematical ideas have a vague feeling that there are infinities and infinities, that the term infinity as attached to the natural sequence of numbers, and the term infinity used in connection with points on a line are essentially different. This vague idea, which we have the contents of an infinite collection, may be compared to a net. It is as if we threw a net of unit mesh and so singled out the whole numbers, all other numbers passing through. We then took a second net of mesh, 1/10, then a third of mesh, 1/100th, and continuing this way we gathered up more and more of the rational numbers. We conceive of no limit to the refinement of this process, for no matter how fine a net we may cast, there is yet a finer that could be cast. Give free rein to your imagination, and you can picture this ultra-ultimate net so compact, of mesh so fine, as to be able to gather up all the rational numbers. It is when we push this analogy to the extreme and begin to regard this limiting net as something fixed, frozen as it were, that we strike all the difficulties so skillfully brought out by Zeno. Here, however, we are concerned with another difficulty. This ultra-ultimate rational net, even if it could be materialized, would still be incapable of gathering all numbers. A net still more compact is necessary to take care of the irrationals of algebra, and even this algebraic net would be incapable of gathering the transcendental numbers. And thus our intuitive idea is that the rational number domain is more compact than the natural, that the algebraic numbers are arranged in still denser formation, and that finally the real number domain, the arithmetic continuum, is the ultra-dense medium, a medium without gaps, a network of mesh zero. If then we are told for the first time that George Cantor made an actual attempt to classify infinite collections and to endow each with a number representative of its plurality, we naturally anticipate that he succeeded in finding a measure of this variable compactness. And just because such were our anticipations, the achievement of Cantor has many surprises in store for us, some of these so striking as to border on the absurd. The attempt to measure the compactness of a collection by means of nets is doomed to failure because it is physical in principle and not arithmetical. It is not arithmetical because it is not built on the principle of correspondence on which all arithmetic rests, the classification of the actually infinite, i.e., of the various types of plurality of infinite collections, if such a classification is at all possible, must proceed on the lines along which pluralities of finite collections were classified. Now we saw in the opening chapter that the notion of absolute plurality is not an inherent faculty of the human mind. The genesis of the natural number, or rather of the cardinal numbers, can be traced to our matching faculty, which permits us to establish correspondence between collections. The notion of equal, greater, less precedes the number concept. We learn to compare before we learn to evaluate. Arithmetic does not begin with numbers, it begins with criteria. Having learned to apply these criteria of equal, greater, less, man's next step was to devise models for each type of plurality. These models are deposited in his memory very much as the standard meter is deposited at the Bureau of Longitudes in Paris. 1, 2, 3, 4, 5 ellipses. We could just as well have had eye, wings, clover, legs, hand, ellipses, and, for all we know, the latter preceded our present form. The principle of correspondence generates the integer, and through the integer dominates all arithmetic. And, in the same way, before we can measure the plurality of infinite collections, we must learn to compare them. How? in the same way that this was accomplished for finite collections. The matching process, which performed such signal services in finite arithmetic, should be extended to the arithmetic of the infinite, for the elements of two infinite collections might also be matched, one by one. The possibility of establishing a correspondence between two infinite collections is brought out in one of the dialogues of Galileo, the first historical document on the subject of infinite aggregates. I reproduce this dialogue verbatim from a book entitled Dialogues Concerning the New Sciences, which appeared in 1636. 3 persons participate in the dialogues. Of these, Sagredo represents the practical mind, Simplicio one who is trained in scholastic methods, while Salviati is obviously Galileo in person. Salviati. This is one of the difficulties which arise when we attempt with our finite minds to discuss the infinite, assigning to it those properties which we give to the finite and limited. But this I think is wrong, for we cannot speak of infinite quantities as being the one greater or less than or equal to the other. To prove this, I have in mind an argument which for the sake of clearness I shall put in the form of questions to Simplicio, who raised this difficulty. I take it for granted that you know which of the numbers are squares and which are not. Simplicio. I am quite aware that a square number is one which results from the multiplication of another number by itself. Thus, 4, 9, etc. are square numbers which come from multiplying 2, 3, etc. by themselves. Salviati. Very well. And you also know that just as the products are called squares, so the factors are called sides or roots, while on the other hand, those numbers which do not consist of 2 equal factors are not squares. Therefore, if I assert that all numbers, including both squares and non-squares, are more than the squares above, I shall speak the truth. Shall I not? Simplicio. Most certainly. Salviati. If I ask how many squares there are, one might reply truly that there are as many as the corresponding numbers of roots, since every square has its own root, and every root its own square, while no square has more than one root, and no root more than one square. Simplicio. Precisely so. Salviati. But if I inquire how many roots there are, it cannot be denied that there are as many as there are numbers, because every number is a root of some square. This being granted, we must say that there are as many squares as there are numbers, because they are just as numerous as their roots, and all the numbers are roots. Yet, at the outset, we have said that there are many more numbers than squares, since the larger portion of them are not squares. Not only so, but the proportionate number of squares diminishes as we pass to larger numbers. Thus up to 100 we have 10, i.e. the squares constitute 1/10 of all numbers. Up to 10,000 we find only 1/100th part to be squares, and up to 1,000,000 only 1,000th part. And yet on the other hand, in an infinite number, if one could conceive of such a thing, he would be forced to admit that there are as many squares as there are numbers all taken together. Sagredo. What then must one conclude under such circumstances? Salviati. So far as I see, we can only infer that the number of squares is infinite and the number of their roots is infinite. Neither is the number of squares less than the totality of all numbers, nor the latter greater than the former. And finally, the attributes equal, greater, and less are not applicable to infinite, but only to finite quantities. When, therefore, Simplicio introduces several lines of different lengths, and how it is possible that the longer ones do not contain more points than the shorter, I answer him that one line does not contain more or less, or just as many points as another, but that each line contains an infinite number. The paradox of Galileo evidently left no impression on his contemporaries. For 200 years nothing was contributed to the problem. Then, in 1820, there appeared a small tract in German by one Bolzano, entitled The Paradoxes of the Infinite. This, too, attracted little attention, so little indeed that when 50 years later the theory of aggregates became the topic of the day, few mathematicians knew who the man was. Today, Bolzano's contributions are of a purely historical interest. While it is true that he was the first to broach the question of the actually infinite, he did not go far enough. Yet, due honor must be given the man for creating the all-important concept of the power of an aggregate, of which I shall speak shortly. The modern theory of aggregates begins with George Cantor. His essay, which laid the foundation of this new branch of mathematics, appeared in 1883 under the title On Linear Aggregates. This essay was the first to deal with the actually infinite as with a definite mathematical being. The following passage from this essay will bring out clearly Cantor's approach to the problem. Quote, "It is traditional to regard the infinite as the indefinitely growing, or in the closely related form of a convergent sequence, which it acquired during the 17th century. As against this I conceive the infinite in the definite form of something consummated, something capable not only of mathematical formulations, but of definition by number. This concept of the infinite is opposed to traditions which have grown dear to me, and it is much against my own will that I have been forced to accept this view. But many years of scientific speculation and trial point to these conclusions as to a logical necessity, and for this reason I am confident that no valid objections could be raised which I would not be in position to meet." End quote. To appreciate the great courage which it required to break so openly with the traditions of the past, we must understand the universal attitude of Cantor's generation towards the actually infinite. For this purpose I quote from a letter of the great Gauss to Shoemaker, which, although written in 1831, set the tone of the mathematical world for the next half-century. Quote, "As to your proof, I must protest most vehemently against your use of the infinite as something consummated, as this is never permitted in mathematics. The infinite is but a figure of speech, an abridged form for the statement that limits exist which certain rations may approach as closely as we desire, while other magnitudes may be permitted to grow beyond all bounds. No contradictions will arise as long as finite man does not mistake the infinite for something fixed, as long as he is not led by an acquired habit of the mind to regard the infinite as something bounded." End quote. Gauss's ideas on the subject were universally shared, and we can imagine what a storm Cantor's open defiance raised in the camp of the orthodox. Not only that the actually infinite was not in one guise or another used in the days of Cantor, but that in such matters the traditional attitude was like that of the Southern gentleman with respect to adultery. He would rather commit the act than utter the word in the presence of a lady. It was fortunate for Cantor that mature reflection had thoroughly steeled him to face the onslaught, because for many years to come he had to bear the struggle alone. And what a struggle! The history of mathematics has not recorded anything equal to it in fury. The story beginnings of the theory of aggregates show that even in such an abstract field as mathematics, human emotions cannot be altogether eliminated. Cantor begins where Galileo left off. Yes, it is possible to establish a correspondence between two infinite collections, even if one is but a part of the other. For precision, therefore, let us say that two collections, finite or infinite, are equivalent, or have the same power, if they can be matched element for element. If two collections are of different power, then the matching process will exhaust one, but there will still remain unmatched elements in the other. In other words, the first may be matched with a part of the second, but the second cannot be matched with any part of the first. Under the circumstances, we say that the second aggregate is of a power greater than the first. If A and B are two finite collections, each containing the same number of elements, then obviously they have the same power. And conversely, if A and B are finite collections of equal power, they have also the same cardinal number. If A and B are of unequal power, then to the greater power corresponds also the greater cardinal number. For finite collections, therefore, the concept of power can be identified with that of cardinal number. Now, since in the arithmetic of the finite, the term power can be identified with cardinal number, it is natural to inquire whether it is possible to identify the powers of infinite collections with numbers of a higher order, transfinite numbers as it were, and by means of this new concept create a transfinite arithmetic, an arithmetic of the infinite. If we proceed along the lines suggested by the beginnings of finite arithmetic, we must seek model aggregates, each model representative of some typical plurality. Such models are close at hand: the natural sequence, the rational domain, the field of algebraic numbers, the arithmetic continuum, all these infinite collections which have grown so familiar to us through constant use are admirably adapted as standards of comparison. Let us then endow these standard collections with symbols, and have these symbols play the same role in a transfinite arithmetic as their counterparts, the finite cardinal numbers 1, 2, 3, etc., play in the arithmetic of the finite. These symbols Cantor calls the transfinite cardinals. He orders them in a sequence of growing power. He defines the operations of addition, multiplication, and potentiation upon these abstract beings. He shows how they combine among themselves and with finite cardinals. In fine, these illusory creatures of Cantor's genius possess so many of the properties of finite magnitudes that it seems altogether proper to confer upon them the title number. But one all-important property they do not possess, and that is finitude. This last statement sounds like a truism, and yet it is not intended in any spirit of triviality. All the paradoxical propositions which I am about to present derive from the fact that these mathematical beings, which have all the appearances of numbers, are deprived of some of the most rudimentary attributes of common number. One of the most striking consequences of this definition is that a part of a collection is not necessarily less than the whole. It may be equal to it. The part may have the power of the whole. This sounds more like theology than mathematics, and indeed we find this idea being toyed with by many a theologian and near-theologian. In the Sanskrit manuals, where religion is so delightfully intermixed with philosophy and mathematics and sex instruction, such ideas are quite usual. Thus Bhaskara, in speculating on the nature of the number 1 divided by 0, states that it is like the infinite and variable God who suffers no change when old worlds are destroyed or new ones created, when innumerable species of creatures are born or as many perish. The part has the power of the whole." End quote. Such is the essence of Galileo's paradox. But while Galileo dodged the issue by declaring that, quote, "the attributes of equal, greater, and less are not applicable to infinite, but only to finite quantities," end quote, Cantor takes the issue as a point of departure for his theory of aggregates. And Dedekind goes even further. To him, it is characteristic of all infinite collections that they possess parts which may be matched with the whole. For purposes of illustration, consider any infinite sequence ordered and labeled accordingly. Now drop any finite number of terms in the beginning and relabel the curtailed sequence. For every term of the second, there was a term in the original sequence of the same rank, and vice versa. The correspondence is, therefore, complete, and the two sequences possess the same power, and yet it cannot be denied that the second is but a part of the first. Such a phenomenon is possible only in infinite collections, for it is characteristic only of finite collections that the whole is never equal to a part. But let us return to the Cantor theory. The symbol A will designate the power of the aggregate of natural numbers. Any aggregate which possesses the power A will be called denumerable. The sequence of perfect squares used in Galileo's argument is such a denumerable aggregate, but so is every other sequence, for the mere fact that we can assign a rank to any term shows that there is a perfect correspondence between the sequence and the natural numbers. The even numbers, the odd numbers, any arithmetic progression, any geometric progression, any sequence at all, is denumerable. What is more, if any such sequence is imagined removed from the domain of natural numbers, the remaining aggregate is still infinite and still denumerable. And this is why there is no hope of reducing the power of a denumerable set by a thinning out process. We may, for instance, remove all even numbers, then all remaining multiples of 3, then all remaining multiples of 5. We may continue this process indefinitely without affecting the power of what remains. In the language of Cantor, there is no smaller transfinite number than the number A, which measures the plurality of any denumerable infinite collection. But if there be no hope of obtaining a smaller transfinite by thinning out the natural sequence, could we not increase the power by a process of filling in? It would appear, indeed, that the power of the rational domain, which is everywhere dense, should be greater than that of the natural sequence which is discrete. Here again our intuition leads us astray. For Cantor proves to us that the rational aggregate is also denumerable. To prove this, it is only necessary to show that the rational numbers can themselves be arranged in a sequence, by assigning to each rational number a definite rank. This is what Cantor actually does. We can get a general idea of the method by considering it geometrically. In the accompanying figure, we have two sets of parallel lines at right angles to each other. We identify any line of the horizontal set by a whole number y, the number y taking on all integral values from -infinity to +infinity. Similarly for the number x, which identifies the vertical lines. Now we label any joint of the infinite lattice we have thus erected by the two numbers which identify the vertical and the horizontal lines there intersecting. Thus the symbol y, x identifies a determinate joint in our lattice work, and conversely any point is capable of such a representation. We shall show that the totality of these joints form a denumerable aggregate. To prove this striking fact, it is sufficient to draw the spiral-like polygonal line as in the figure and follow the joints in the order in which they appear on the diagram. On the other hand, we can identify the symbol y, x with the fraction y over x, but if we do this, it is obvious that we cannot label all our joints with distinct rational numbers. In fact, all joints situated on the same line through the origin represent one and the same rational number, as it is easy to convince oneself. To eliminate this ambiguity, we agree to count each fraction only the first time it occurs. These points form the sequence 1, 0, -1, -2, 2, +1/2, -1/2, -3/2, -3, +3, +3/2, +2/3, +1/3, etc. Here all rationals are represented, and each rational occurs in the sequence but once. The domain of rational numbers is therefore denumerable. But, the reader may exclaim, this stands in direct contradiction to our notion of compactness, according to which no rational number has a successor. Between any two rational numbers, we can insert an infinity of others. But here we have actually established a succession. The answer to this is that, while we have here a true succession, it is not of the same type as the natural succession, 1, 2, 3, etc., which is arranged according to magnitude. We succeeded in enumerating the rational numbers because in the new arrangement, we were not obliged to preserve the order of magnitude. We have obtained succession at the expense of continuity. We see that it is essential to discriminate between two kinds of equivalence. From the standpoint of correspondence, two collections are equivalent if they can be matched element by element. From the standpoint of order, this is also indispensable. But for complete equivalence, for similarity, it is necessary in addition that the matching process should not destroy the order of arrangement, i.e., if in the collection A the element a preceded the element a prime, then in the collection B the corresponding element b must precede b prime. The aggregate of rational numbers arranged according to magnitude and the spirally arranged aggregate by means of which we denumerated the rational numbers are equivalent from the standpoint of correspondence, but not from the standpoint of order. In other words, They have the same cardinal number, lowercase a, but are of different ordinal types. Hence, Cantor proposed a theory of ordinal types which form the counterpart of the ordinal numbers of finite arithmetic. Theorem, however, we had the fundamental property that any two collections with equal cardinal numbers had also the same ordinal number, and to this we owed the facility with which we passed from one to the other. But in the Cantor arithmetic of the infinite, two aggregates may be measured by the same cardinal number and yet be ordinally distinct, or, as Cantor says, dissimilar. Thus, mere compactness is no obstacle in denumeration, and the filling-in process does not affect the power of an aggregate any more than the thinning-out process did. So the next Cantor deduction is somewhat less of a shock to us. This states that the aggregate of algebraic numbers is also denumerable. Cantor's proof of this theorem is a triumph of human ingenuity. He commences by defining what he calls the height of an equation. This is the sum of the absolute values of the coefficients of the equation, to which is added its degree diminished by 1. For instance, the equation 2x cubed minus 3x squared plus 4x minus 5 equals 0 has a height h equals 16, because 2 plus 3 plus 4 plus 5 plus bracket 3 minus 1 bracket equals 16. He proves next that there are but a finite number of equations which admit any positive integer h for height. This permits us to order all algebraic equations in groups of increasing height. It can be shown that there is only one equation of height 1, 3 of height 2, 22 of height 3, etc. Now, within each group of given height, we can order the equations by any number of schemes. For instance, we can combine all equations of the same degree into one subgroup and arrange each subgroup according to the magnitude of the first coefficients, for those which have the same first coefficient according to the second, etc., etc. Any such scheme would allow us to order all algebraic equations into a hierarchy and thus enumerate them, i.e., assign to each equation a rank. Now, to every one of these equations may correspond one or more real roots, but the number is always finite, and in fact cannot exceed the degree of the equation, and therefore cannot exceed the height. These roots can again be arranged according to their magnitude. Now, if we consider the scheme as a whole, we shall surely find repetitions, but as in the case of the rational numbers, these repetitions can be avoided by agreeing to count any algebraic number only the first time it occurs in the process. In this manner, we have succeeded in assigning to any algebraic number a rank in the hierarchy, or in other words, we have denumerated the aggregate of algebraic numbers. By this time, the suspicion will have grown upon the reader that perhaps all aggregates are denumerable. If such were the case, there would be but one transfinite, and what was true for the rational and the algebraic aggregates would be generally true even of the continuum. By some artifice, such as Cantor's height, any infinite collection could be arranged into a hierarchy and thus enumerated. Such indeed was Cantor's idea in the early stages of his work. To enumerate the real numbers was one of the points of his ambitious program, and the theory of transfinite numbers owes its birth to this attempt to count the continuum. That such is not the case, that it is not possible to arrange all real numbers in a denumerable sequence, was known to Cantor as early as 1874. However, the proof of it did not appear until 1883. I cannot go into the details of this demonstration, the general principle of which consists in assuming that all real numbers have been erected into a hierarchy, and then in showing, by a method which we now call the diagonal procedure, that it is possible to exhibit other numbers which, while real, are not among those which have been enumerated. One sidelight on this proof has an important historical bearing. The reader will remember Louisville's discovery of transcendentals. This existence theorem of Louisville was re-established by Cantor as a sort of byproduct of his theorem that the continuum cannot be denumerated. The relative wealth of the two domains, the algebraic and the transcendental, a question which to Louisville had only a vague meaning, was now formulated by Cantor in full rigor. He showed that whereas the algebraic domain has the power A of the aggregate of natural numbers, the transcendentals possess the power C of the continuum. Thus the contention that there are incomparably more transcendentals than algebraic numbers acquires a true significance. And here too, in this domain of real numbers, the part may have the power of the whole. In the quaint language of Galileo, quote, "The longer line contains no more points than the shorter." End quote. In fact, a segment of a line, no matter how short, has the same power as the line indefinitely extended. An area, no matter how small, has the power of the infinite space of 3 dimensions. In short, parceling or piecing together can no more affect the power of an aggregate than thinning out or filling in. At this point, our intuition again whispers a suggestion. How about these manifolds of higher dimensions? The complex number domain, which we identified with the set of points in the plane, the points in space, the vectors and quaternions, the tensors and the matrices, and other intricate complexes which mathematicians manipulate as though they were individuals, subject to the laws of operations on numbers, but which cannot be represented in a continuous manner as points on a line. Surely these manifolds should have a power higher than that of the linear continuum. Surely there are points in space of 3 dimensions, this universe extending indefinitely in all directions, than on a segment of a line 1 inch long. This, too, may have been an early idea of Cantor, but he proved conclusively that here too our intuition leads us astray. The infinite manifold of 2 or 3 dimensions, the mathematical beings which depend on a number of variables greater even than 3, any number in fact, still have no greater power than the linear continuum. Nay, even could we conceive of a variable being whose state at any instant depended on an infinite number of independent variables, a being which lived in a world of a denumerable infinite of dimensions, the totality of such beings would still have a power not greater than that of the linear continuum, not greater than a segment 1 inch long. This statement strikes us as being in such direct contradiction with our ideas of dimension as to be absurd. Such was, indeed, the opinion of many when Cantor first announced it, and there were first-class minds who took it warily, to say the least. But Cantor's proof of this fundamental proposition is so simple that even a bright child can see it. I shall illustrate the statement as it applies to the points in the plane. The reader will see that the argument is perfectly general. Since the points within a segment of length 1 have the same power as the indefinite line, and the points within the square of side 1 the same power as the indefinite plane, it will be sufficient to show that a 1-to-1 correspondence can be established between this square and this segment. Now any point P within this square OAFB of the accompanying figure can, as we saw, be represented by means of 2 coordinates x and y. These latter are real numbers not exceeding 1, and can be exhibited as proper decimal fractions. These fractions can be always regarded as interminable, for even if terminable, they may be rendered interminable by an adjunction of zeros behind the last significant figure. Let us then write these decimal fractions in the form x equals a subscript 1 order a subscript 2 order a subscript 3 order a subscript 4, etc., and y equals b subscript 1 order b subscript 2 order b subscript 3 order b subscript 4, etc. Now let us form a third decimal fraction z by taking alternately the figures x and y. Z equals interpunct a subscript 1, order b subscript 1, order a subscript 2, order b subscript 2, order a subscript 3, order b subscript 3, order a subscript 4, order b subscript 4, etc. This fraction again represents a real number, and we can exhibit it as a point Q on the segment OC. The correspondence thus established between P and Q is reciprocal and unique. For given x and y, we can always form z, and in only one way, and conversely, the knowledge of z permits us to reconstruct the numbers x and y and therefore the point P. What lies between and what lies beyond? There is nothing in the Cantor theory to preclude the possibility of a transfinite number greater than a, but less than c. Yet all known point aggregates are either denumerable, like the rational or algebraic number domains, or else, like the transcendentals, have the power of the arithmetic continuum. All attempts to erect an artificial point aggregate, which would be mightier than the natural sequence, but less mighty than the aggregate of the points on a line, have so far not been crowned with success. On the other hand, aggregates are known which have a power greater than c. Among these there is the so-called functional manifold, i.e. the totality of all correspondences which can be established between two continua. This totality cannot be matched with the natural numbers. The corresponding cardinal number is denoted by f. Again, there is nothing in the theory that would preclude the existence of cardinals between c and f, and yet no aggregate has yet been discovered of power less than f, but greater than c. And beyond f there are still greater cardinal numbers, the same diagonal procedure which permits us to derive the functional space from the continuum can be used to derive from the functional space a superfunctional which cannot be matched with the aggregate of correspondences. Aggregates of higher and higher power can be thus erected, and the process cannot conceivably be terminated. So pushed to its ultimate border, the Cantor theory asserts that there is no last transfinite number. This assertion is strangely similar to the other. There is no last finite number, yet the latter was admittedly an assumption, the fundamental assumption of finite arithmetic, whereas the analogous statement in the arithmetic of the infinite seems to be the logical conclusion of the whole theory. There is no last transfinite. The proposition sounds innocent enough, and yet it contained within itself an explosive which nearly wrecked the whole theory, and that at a time when Cantor, having overcome the powerful resistance of his first opponents, had all reason to believe that his principles had emerged triumphant. For almost simultaneously a series of phenomena were uncovered which, while seemingly different in character, indicated that something was wrong. The Italian Burali Forti, the Englishman Bertrand Russell, the German Koenig, and the Frenchman Richard unearthed antimonies and paradoxes which bear their respective authors' names. Again, the question was raised as to the validity of the Cantor methods and deductions, as to the legitimacy of the use of the actually infinite in mathematics. It would take me too far to go into detail about the nature of the contradictions discovered. Heterogeneous though these paradoxes are, they all seem to hinge on the questions how the word all should be used in mathematics, if it is to be used at all. If this word can be used freely in connection with any conceivable acts of the mind, then we can speak of the aggregate of all aggregates. If now this is an aggregate in the Cantor sense, then it too must possess a cardinal number. This transfinite number is the greatest conceivable, for can we conceive of an aggregate mightier than the aggregate of all aggregates? This cardinal is, therefore, the last transfinite, the truly ultra-ultimate step in the evolution of the abstraction which we call number, and yet there is not last transfinite. Much water has passed under the bridge since these paradoxical questions were first raised. Many solutions have been offered. Thousands of essays have been written on both sides of the question, much sarcasm indulged in by the Cantorians and their opponents. Yet the question remains wide open. Cantor found mathematics undivided. He left it split into two contending camps. To present the platforms of these opposing mathematical parties with the simple means at my disposal, and pledged as I am to avoid technicalities, is impossible. And yet I should fall short of my own program were I to pass up entirely this most vital issue of modern mathematics. So I shall simply and briefly state the dilemma as voiced by the chief representatives of the opposing camps. On the side of the formalists are Hilbert, Russell, Zermelo. While defending Cantor, they are Mensheviki, in the sense that they are attempting to save his minimum program. They admit that the unrestricted use of the words all, aggregate, correspondence, and number is inadmissible. But the solution lies not in the complete negation of the theory of aggregates, but in the remolding of the theory along the lines of pure reason. We must devise a body of axioms which could serve as the basis of the theory, and, to make sure that we are not again led astray by our institution, we must construct a purely formal, logically consistent, schematic outline of such a body, a mere skeleton without content. Having erected such a comprehensive, consistent system, we shall base the arithmetic of the infinite upon it as a foundation, secure in our conviction that no paradox or antimony will ever arise again to disturb our peace of mind. Says Hilbert, quote, "From the paradise created for us by Cantor, no one will drive us out." End quote. The intuitionists, beginning with Kronecker and reinforced by Poincaré, who in our own day are represented by such great minds as Brouwer in Holland, Weil in Germany, and to a certain extent by Borel in France, have a different story to tell the definition of an aggregate. The disease antedates Cantor. It is deep-seated, and the whole body mathematical is affected. Says Weil, quote, "We must learn a new modesty. We have stormed the heavens, but succeeded only in building fog upon fog, a mist which will not support anybody who earnestly desires to stand upon it. What is valid seems so insignificant that it may be seriously doubted whether analysis is at all possible." End quote. To the intuitionists, the issues go far beyond the confines of the theory of aggregates. They maintain that in order that a concept may gain admission into the realm of mathematics, it is not enough that it be well defined. It must be constructible. Not merely must the concept exist in name, but also an actual construction should be given to determine the object which the concept represents. As to construction, the only admissible ones are the finite processes, or, and this is indeed a compromise, such infinite processes as are reducible to finite by means of a finite number of rules. The act of conceiving simultaneously an infinite number of single objects, and of treating the whole as an individual object, does not belong to this category of admissible concepts, and must a priori be barred from arithmetic. And not only does this mean the scrapping of the theory of aggregates, but even the concept of irrational numbers must undergo a profound modification until analysis is purged of all the impurities with which the indiscriminate use of the infinite has polluted it. For, says Weil, mathematics, even to the logical forms in which it moves, is entirely dependent on the concept of natural number. End quote. While this conflict as to the validity of the foundation on which analysis rests is in full blast, the structure itself is rising at a prodigious rate. Each year sees advances which in the 19th century would have required the work of decades. Every decade witnesses the opening of new fields of inductive knowledge which voluntarily submits to the penetration of mathematical analysis. And as to physics, which was among the first conquests of analysis, the pancosmos of the relativity theory is but a universe of differential forms, and the discontinuous phenomena of the microcosmos seem to obey the laws of a wave mechanics which to all appearances is just an application of a theory in differential equations. And we see that strange spectacle of men who are loudest in proclaiming that the empire rests on insecure foundations. We see these gloomy deans forsaking from time to time their own councils of alarum to join in the feverish activity of extending the empire, of pushing further and further the far-flung battle line. Of such is the kingdom of logic. From the day on which man miraculously conceived that a brace of pheasants and a couple of days were both instances of the number 2, to this day, when man has attempted to express in numbers his own power of abstraction, it was a long laborious road, and many were the twists and turns. Have we reached an impasse? Must we retrace our steps, or is the present crisis just another of these sharp turns from which, if the future be judged by the past, number will again emerge triumphant, ready to climb to still dizzier heights of abstraction? Chapter 12. The Two Realities. Quote, "We have found a strange footprint on the shores of the unknown. We have devised profound theories, one after another, to account for its origin. At last we have succeeded in reconstructing the creature that made the footprint, and lo, it is our own." End quote. A. S. Eddington. I have come to the end of my narrative. It was my object to survey the present status of the science of number in the light of its past, so it would be proper in the concluding chapter of such a survey to take a glimpse into the future. But the future belongs to the prophets, and I shall respect their prerogative. There remains the ever-present, the issue of reality. This issue has been in the custody of the philosopher since the days when man first consciously attempted to estimate his place in the universe. It is the philosopher's chief preoccupation today. And so I realize fully that by selecting reality as the theme of this concluding chapter, I am encroaching on a field foreign to my training, foreign to my outlook. I concede further that I have nothing to contribute to the old dilemma, nor have I any intention of rehashing what has been said on the issue by philosophers of opposing schools since the days of Socrates. My interest lies exclusively in the position which the science of number occupies with respect to the general body of human knowledge. It is from this viewpoint that I shall consider the relation of the number concept to the reality of our senses, in the hope that this may throw light on the historical role mathematics has played in creating the new reality, the transreality of modern science. Between the philosopher's attitude towards the issue of reality and that of the mathematician there is this essential difference. For the philosopher the issue is paramount, the mathematician's love for reality is purely Platonic. The mathematician is only too willing to admit that he is dealing exclusively with acts of the mind. To be sure, he is aware that the ingenious artifices which form his stock in trade had their genesis in the same impressions which he identifies with crude reality, and he is not surprised to find that at times these artifices fit quite neatly the reality in which they were born. But this neatness the mathematician refuses to recognize as a criterion of his achievement. The value of the beings which spring from his creative imagination shall not be measured by the scope of their application to physical reality. No, mathematical achievement shall be measured by standards which are peculiar to mathematics. These standards are independent of the crude reality of our senses. They are freedom from logical contradictions, the generality of the laws governing the created form, the kinship which exists between this new form and those that have preceded it. The mathematician may be compared to a designer of garments, who is utterly oblivious of the creatures whom his garments may fit. To be sure, his art originated in the necessity for clothing such creatures. But this was long ago. To this day a shape will occasionally appear which will fit into the garment as if the garment had been made for it. Then there is no end of surprise and of delight. There have been quite a few such delightful surprises. The conic sections, invented in an attempt to solve the problem of doubling the altar of an oracle, ended by becoming the orbits followed by the planets in their courses about the sun. The imaginary magnitudes invented by Cardan and Bombelli describe in some strange way the characteristic features of alternating currents. The absolute differential calculus, which originated as a fantasy of Riemann, became the mathematical vehicle for the theory of relativity, and the matrices, which were a complete abstraction in the days of Cayley and Sylvester, appear admirably adapted to the exotic situation exhibited by the quantum theory of the atom. Yet delightful though these surprises may be, their discovery is not the moving force behind the creative work of the mathematician. For him, mathematics is the field in which he can best manifest his personality. Mathematics for mathematics' sake. Quote, "People have been shocked by this formula," said Poincaré, "and yet it is as good as life for life's sake, if life is but misery." End quote. Religion is the mother of the sciences. When the children grew up, they left their mother. Philosophy stayed at home to comfort the lady in her old age. The long association told more on the daughter than on the mother. To this day, the central problems of philosophy smack of theology. It seems to me that what philosophy lacks most is a principle of relativity. A principle of relativity is just a code of limitations. It defines the boundaries wherein a discipline shall move and frankly admits that there is no way of ascertaining whether a certain body of facts is the manifestation of the observata or the hallucination of the observer. A principle of relativity is an act of resignation, and a philosophical principle of relativity would consist in the frank admission of the insolubility of the old dilemma. Has the universe an existence per se, or does it exist only in the mind of man? To the man of science, the acceptance of the one hypothesis or the other is not at all a question of to be or not to be. For from the standpoint of logic, either hypothesis is tenable, and from the standpoint of experience, neither is demonstrable. So the choice will forever remain a matter of expediency and convenience. The man of science will act as if this world were an absolute whole controlled by laws independent of his own thoughts or acts. But whenever he discovers a law of striking simplicity, or one of sweeping universality, or one which points to a perfect harmony in the cosmos, he will be wise to wonder what role his mind has played in the discovery, and whether the beautiful image he sees in the pool of eternity reveals the nature of this eternity, or is but a reflection of his own mind. The philosopher's speculations on reality are of little use to us when we attempt to determine the degree of reality we should attach to the general number concept. Other ways must be found, so much is certain. But first let me dispose of certain ambiguities in terms. The terms used by the mathematician are, after all, words, and belong to the limited vocabulary by means of which man from the earliest days had endeavored to express his thoughts, both mathematical and non-mathematical. Some of these terms, such as geometry and calculus, have lost their original double meaning and are understood by everybody in the specific sense that they have acquired in mathematical practice. Others, however, such as logical and illogical, rational and irrational, finite and infinite, real and imaginary, have to this day retained their multiple meaning. To the mathematician, who rarely ventures into the realm of metaphysics, these words have a very specific and quite unambiguous meaning. To the philosopher who uses these terms as his stock in trade, they have also a very specific but an entirely different meaning. To the man who is neither philosopher nor mathematician, these words have a general and rather vague significance. No difficulty arises until the philosopher makes an attempt to present to the lay public his analysis of the fundamental concepts of mathematics. It is then that the different connotations attaching to such words as infinity or reality lead to hopeless confusion the mind of the layman. This particularly applies to the concepts of real and imaginary. We owe these unfortunate and yet historically unavoidable terms to a philosopher, Descartes. The term imaginary, as applied to the form a plus root negative b, was justifiable then, inasmuch as no concrete substratum could be assigned to these magnitudes. The moment an interpretation of these magnitudes was found, the inadequacy of the term imaginary was realized. This was voiced by Gauss as follows, quote, "That the subject has been treated from such an erroneous point of view and enveloped with such mysterious obscurity is due largely to the inadequate terminology used. If instead of calling +1, -1, root -1, the positive, negative, and imaginary, sometimes even impossible, unities, they had been called, say, the direct, indirect, and lateral unities, this obscurity would have been avoided." End quote. But the protests were largely in vain. The word imaginary had taken deep root. This stability of mathematical terms is phenomenal. It may be due to the conservatism of the mathematician or to his indifference to the choice of words as long as no ambiguity is implied. Be this as it may, eventually the term complex was half-heartedly substituted for imaginary, but to this day both terms are still in use, and as to the word real, a change to a more adequate term has not even been proposed. The use of the term imaginary in this sense is construed by some experts in reality as evidence of the mysticism with which modern mathematics is permeated. They contend that the mathematicians, in selecting these terms, ipso facto admitted the fictitious nature of these magnitudes. To argue thus is about as reasonable as it would be for a mineralogist to speak of the stony character of infinitesimal analysis, because the word calculus signifies a pebble. If there be any unreality in the complex number, it resides not in the name, nor in the use of the symbol √-1. A complex number is just a pair of real numbers regarded as a single individual, and it cannot be more fictitious, or less for that matter, than the real numbers of which it is composed. Therefore, the critique of the reality of the number concept should revert to the real number. Here the philosopher may find ample evidence of that mysticism which he seeks in mathematics. However great be the abstraction to which we owe our notion of natural number, the concept was born in the firm reality of finite collections. It is true that the moment we began to regard these numbers as a totality, we had to bring in the word all, with all its implications. Nevertheless, the concept of infinity as used in rational arithmetic has been confined to the allegation that any number has a successor. The unlimited character of the counting process was invoked only in order that the rules of operation on integers might attain their absolute generality. The infinite was used only as something potential, never as an actuality. The rational number is but a pair of integers and therefore has as much reality as the integer. Had we then avoided, as Kronecker urged us to avoid, the introduction of infinite processes and consequently that of the irrationals, the complex number would be just a pair of rational numbers, and whatever reality or unreality we could ascribe to the rational would also reside in the complex. But in the search for a field in which any equation of algebra would have a solution, we were compelled to legitimize the infinite process, and the so-called real number was the result. We do not confine ourselves any more to using infinity as a figure of speech or as shorthand for the statement that no matter how great a number, there is one greater. The act of becoming invokes the infinite as the generating principle for any number. Any number is now regarded as the ultra-ultimate step of an infinite process. The concept of infinity has been woven into the very fabric of our generalized number concept. The domain of natural numbers rested on the assumption that the operation of adding one can be repeated indefinitely, and it was expressly stipulated that never shall the ultra-ultimate step of this process be itself regarded as a number. The generalization to real numbers not only extended the validity of infinite repetition to any rational operation, it actually abandoned the restriction and admitted the limits of these processes as bona fide numbers. And such is the irony of words, that the so-called real numbers had been attained at the sacrifice of a part of that reality which we attribute to the natural numbers. How real are these infinite processes which endow our arithmetic with this absolute generality, which make it the instrument of our geometrical and mechanical intuition, and through geometry and mechanics permit us to express by number the phenomena of physics and chemistry? Well, if reality be restricted to the immediate experience of our senses, no thinking man, be he mathematician, philosopher, or layman, would attribute reality to the concept. There is, however, the widespread opinion that the validity of the infinite is the inevitable consequence of the progress of the empirical sciences. It would be presumptuous on my part to refute this contention in my own words, when David Hilbert has so eloquently answered it in his famous address in memory of Weierstrass. Quote, "The infinite, no other question has ever moved so profoundly the spirit of man. No other idea has so fruitfully stimulated his intellect. Yet no other concept stands in greater need of clarification than that of the infinite." When we turn to the question, what is the essence of the infinite, we must first give ourselves an account as to the meaning the infinite has for reality. Let us then see what physics teaches us about it. The first naive impression of nature and matter is that of continuity. Be it a piece of metal or a fluid volume, we cannot escape the conviction that it is divisible into infinity, and that any of its parts, however small, will have the properties of the whole. But wherever the method of investigation into the physics of matter has been carried sufficiently far, we have invariably struck a limit of divisibility, and this was not due to a lack of experimental refinement, but resided in the very nature of the phenomenon. One can indeed regard this emancipation from the infinite as a tendency of modern science and substitute for the old adage, natura non facie saltus, its opposite, nature does make jumps. It is well known that matter consists of small particles, the atoms, and that the macrocosmic phenomena are but manifestations of combinations and interactions among these atoms. But physics did not stop there. At the end of the last century, it discovered atomic electricity of a still stranger behavior. Although up to then it had been held that electricity was a fluid and acted as a kind of continuous eye, it became clear then that electricity, too, is built up of positive and negative electrons. Now, besides matter and electricity, there exists in physics another reality, for which the law of conservation holds, namely energy. But even energy, it was found, does not admit of simple and unlimited divisibility. Planck discovered the energy quanta, and the verdict is that nowhere in reality does there exist a homogeneous continuum in which unlimited divisibility is possible, in which the infinitely small can be realized. The infinite divisibility of a continuum is an operation which exists in thought only, is just an idea which is refuted by our observations of nature, as well as by physical and chemical experiments. The second place in which we encounter the problem of the infinite in nature is when we regard the universe as a whole. Let us then examine the extension of this universe to ascertain whether there exists there an infinitely great. The opinion that the world was infinite was a dominant idea for a long time, up to Kant and even afterward. Few expressed any doubt in the infinitude of the universe. Here, too, modern science, particularly astronomy, raised the issue anew and endeavored to decide it not by means of inadequate metaphysical speculations, but on grounds which rest on experience and on the application of the laws of nature. There arose weighty objections against the infinitude of the universe. It is Euclidean geometry that leads to infinite space as a necessity. Einstein showed that Euclidean geometry must be given up. He considered this cosmological question too from the standpoint of his gravitational theory and demonstrated the possibility of a finite world, and all the results discovered by the astronomers are consistent with the hypothesis of an elliptic universe." End quote. So the further we progress in our knowledge of the physical world, or in other words, the further we extend our perceptual world by means of scientific instruments, the more we find our concept of infinity incompatible with this physical world in deed as well as in principle. Since then the conception of infinity is not a logical necessity, and since, far from being sanctified by experience, all experience protests its falsity, it would seem that the application of the infinite to mathematics must be condemned in the name of reality. Such a condemnation would reduce mathematicians to the bounded arithmetic and the bounded geometry which I discussed in the 4th chapter. Quote, "What is valid seems so insignificant that it may be seriously doubted whether analysis is at all possible." End quote. The lofty structure erected by the mathematicians of the last 3 centuries would be razed to the foundation. The principles and methods which derived their power from the use of the infinite would be scrapped. The physical sciences, which have so confidently applied the concepts of limit and function and number in formulating and analyzing their problems, would turn over a new leaf. They would rebuild their foundations and devise new instruments in lieu of those condemned. All this in the name of reality. It is a drastic program, to be sure. But after this revision has been effected, what little remained of mathematics after this purging process has been consummated would be in perfect consonance with reality. Would it? That is the question, and this question is tantamount to another. What is reality? In asking this latter, we are not at all concerned with hair-splitting definitions or with quibbling about irrelevant issues. We are concerned only with the scope we should assign to this reality, which from now on must serve as the criterion as to what is valid and what is not valid. We naturally turn to the experts in reality. Each one is offering us his particular brand of reality. But as to the reality, there seems to be no such thing. We are in the state which the French so expressively describe as embarras du choix. 2 of these brands are of particular interest to us: the subjective reality and the objectivity reality. The subjective reality seems to be what could be described as the aggregate of all the sense impressions of an individual. As to objective reality, the definition varies with each philosophical school, for it is precisely here that the dilemma of the existence or the non-existence of a world outside of our consciousness is brought to a climax. Stripped of all its metaphysical irrelevancies and free of philosophical jargon is this description by Poincaré. Quote, "What we call objective reality is, in the last analysis, what is common to many thinking beings and could be common to all." End quote. In spite of its vagueness, in spite of the obvious weakness of the phrase, "what could be common to all," this is the nearest we can get to this intuitive idea of reality which we all seem to possess. Now the difficulty in determining a valid scope of reality lies precisely in the fact that no individual can successfully separate this subjective reality, which is the aggregate of his personal sense impressions, from the objective reality which he has acquired from contact with other individuals, present or past. Studies in the psychology of primitive peoples may throw considerable light on this question, but here too environment did its work. The nearest we can come to grasping this subjective reality is the psychology of an infant, and since we cannot successfully reconstruct our own impressions as infants, we must rely on the studies which adults have made on infants, studies which are invariably colored by preconceived notions. But let us assume that the subjective reality of an individual can be identified with the data which physiologists and psychologists of the type of Helmholtz or Mach have obtained with regard to the perceptions of sight, sound, touch, etc. If the scope of this reality be taken as the criterion of validity, the unavoidable verdict would be that even the emaciated arithmetic, which was the residue left after purging mathematics from the infinite, must undergo further amputations, for the counting process is not a part of this reality. The counting process presupposes a different reality, an objective reality, this term being interpreted in the sense Poincaré used it. Counting presupposes the human ability to classify various perceptions under the same head and to endow the class with a name. It presupposes the ability to match 2 collections, element for element, and to associate these collections with a number word, which is but the model for a given plurality. It presupposes the ability to order these models into a sequence and to evolve a syntax which will permit an indefinite extension of these number words. In short, the counting process postulates the existence of a language, an institution which transcends the subjective reality or the immediate perceptions of any individual. If then this subjective reality be taken as criterion of what is valid in mathematics, we should be compelled not only to condemn the infinite process and all it implies, but to scrap the counting procedure as well. The primitive sense, such as some birds and insects possess, would be the only legitimate field for number, and along with our language and arithmetic, we should have to scrap the whole intricate structure of civilization which has been erected on these two human institutions. Of the absolute and immutable world which exists outside our consciousness we know only through theological speculations. Accepting it or rejecting it are alike futile to a natural philosophy. But just as futile and sterile is the acceptance of the crude reality of our senses as the arch-reality, the only reality, it is convenient for a systematic exposition, to be sure, to regard the newly born child, or the primitive man, or the animal, as the embodiment of such an arch-reality. We can go still further and imagine, as did Helmholtz, Mach, and Poincaré, an intelligent being who has been deprived of all but one of his senses, say sight, and speculate on the type of universe that such a being would construct. Such speculations are tremendously fascinating in that they allow free rein to our power of resolving our sensations into their constituents, and then regarding the concept as a synthesis of these arch-sensations. But to accept such a synthesis as reality, as the reality, has, to my way of thinking, one fatal defect. It postulates the existence of an individual intellect, whereas the very process of coordinating these sensations involves thought, which is impossible without the vehicle language, which in turn implies an organized exchange of impressions, which in turn presupposes a collective existence for human beings, some form of social organization. The only reality that can be taken as a criterion of validity is not that absolute, immutable reality which exists outside of our consciousness and is therefore pure metaphysics, nor that arch-reality which the physiologist and the psychologist manage to isolate by means of painstaking experiments. It is rather that objective reality which is common to many and could be common to all. And that reality is not a collection of frozen images, but a living, growing organism. But when we turn to this objective world with a view of finding there a criterion for the reality of mathematical concepts, we strike a new difficulty. These things common to many may be confined to those immediate impressions of an individual which are shared by other thinking beings, but they may also include all the data which the race has acquired through the application of scientific instruments, for such facts, too, are common to many and could presumably be common to all. Now this latter extended world may be valid for judging the reality of any qualitative statement. But the moment we attempt to use it as a criterion for number, we are confronted with the fact that this objective world presupposes number, because our scientific instruments are designed, built, and used according to fixed mathematical principles which, in turn, rest on number. Indeed, whether we use a ruler or a weighing balance, a pressure gauge or a thermometer, a compass or a voltmeter, we are always measuring what appears to us to be a continuum, and we are measuring it by means of a graduated number scale. We are then assuming that there exists a perfect correspondence between the possible states within this continuum and the aggregate of numbers at our disposal. We are tacitly admitting an axiom which plays within this continuum the role which the Dedekind-Cantor axiom plays for the straight line. Therefore, any measuring device, however simple and natural it may appear to us, implies the whole apparatus of the arithmetic of real numbers. Behind any scientific instrument there is the master instrument, arithmetic, without which the special device can neither be used nor even conceived. This is then the difficulty. If we were to judge the reality of the real number by the objective world which contains all the data derived by means of scientific instruments, we should be moving in a vicious circle, because these instruments already postulate the reality of the real number. Nor would we avoid the vicious circle if we were to confine ourselves to the more restricted objective world of those of our immediate impressions that are shared by others. For let us ban all measuring devices, let us declare public opinion the sole criterion of reality. How shall we then arrive at a valid judgment? When you declare that I am colorblind because I see green where you see red, how will you demonstrate the truth of your assertion, if not by an appeal to majority rule? Here too, then, we have both agreed to leave the decision to number. Figures do not lie, because they cannot lie. They cannot lie because they have been declared a priori infallible. Having elected number as the sole arbiter for judging values, having agreed to abide by its decisions, we have ipso facto waived our right of appeal to any other tribunal. What is the conclusion? An individual without a milieu, deprived of language, deprived of all opportunity to exchange impressions with his peers, could not construct a science of number. To his perceptual world, arithmetic would have no reality, no meaning. On the other hand, the objective world of a thinking being is made up of those impressions which are shared by the majority of his peers. To him the question, what reality shall we ascribe to number, is meaningless, because there is no reality without number, as there is no reality without space or without time. And so neither in the subjective nor yet in the objective world can we find a criterion for the reality of the number concept, because the first contains no such concept, and the second contains nothing that is free of the concept. How then can we arrive at a criterion? Not by evidence, for the dice of evidence are loaded, not by logic, for logic has no existence independent of mathematics. It is only one phase of this multi-phased necessity that we call mathematics. How then shall mathematical concepts be judged? They shall not be judged. Mathematics is the supreme judge. From its decisions there is no appeal. We cannot change the rules of the game. We cannot ascertain whether the game is fair. We can only study the player at his game, not, however, with the detached attitude of a bystander, for we are watching our own minds at play. I recall my own emotions. I had just been initiated into the mysteries of the complex number. I remember my bewilderment. Here were magnitudes patently impossible and yet susceptible of manipulations which lead to concrete results. It was a feeling of dissatisfaction, of restlessness, a desire to fill these illusory creatures, these empty symbols, with substance. Then I was taught to interpret these beings in a concrete geometrical way. There came then an immediate feeling of relief, as though I had solved an enigma, as though a ghost which had been causing me apprehension turned out to be no ghost at all, but a familiar part of my environment. I have since had many opportunities to realize that my emotions were shared by many other people. Why this feeling of relief? We have found a concrete model for these symbols. We have found that we can attach them to something familiar, to something that is real, or at least seems real. But why consider a point in the plane, or rather the segments measuring the distances of such a point from two arbitrary axes of references? Why consider this more real than the quantity A plus IB? What reality is there behind a plan, a line, a point? Why, only a year or two before, these too were but phantoms to me. The plane extending indefinitely in all directions, my nearest approximation of this was a sheet of paper, 8 inches by 11, or a wavy blackboard full of ridges and scratches. The line deprived of thickness, the point of intersection of two such lines, a thing without dimension, a pure illusion, for which there existed no model whatsoever, and finally the coordinates of such a point, which involved all the uncertainties, all the inaccuracies of measurement, were such things the concrete reality that caused my feeling of grief? We have attached a phantom to a fiction, which had this advantage over the phantom that it was a familiar fiction, but it had not always been familiar. There was a time when this too caused bewilderment and restlessness, until we attached it to a still more primeval illusion, which in turn had been rendered concrete through centuries of habit. The reality of today was but an illusion yesterday. The illusion survived because it helped to organize and systematize and guide our experience, and therefore was useful to the life of the race. Such is my interpretation of the words of Nietzsche. Quote, "We hold mere falsity no ground for rejecting a judgment. The issue is, to what extent has the conception preserved and furthered the life of the race? The falsest conceptions, and to these belong our synthetic judgments a priori, are also those which are the most indispensable. Without his logical fictions, without measuring reality in a fictitious absolute and immutable world, without the perpetual counterfeiting of the universe by number, man could not continue to live. The renunciation of all false judgment would mean a renunciation, a negation of life." End quote. It is not the immediate evidence nor the laws of logic that can determine the validity of a mathematical concept. The issue is, how far does the concept preserve and further the intellectual life of the race? That is why the alarming reports of the gloomy deans leave me unalarmed. The criterion of validity for any illusion is a post factum and sometimes a post mortem judgment. Those that preserve and further the life of the race thrive and grow, and thus earn their right to reality. Those that are harmful or useless eventually find their way to the textbooks on metaphysics and theology, and there they stay. So they, too, do not die in vain. Experimental evidence and logical necessity do not exhaust the objective world which we call reality. There is a mathematical necessity which guides observation and experiment, and of which logic is only one phase. The other phase is that intangible, vague thing which escapes all definition, and is called intuition. And so, to return to the fundamental issue of the science of number, the infinite. The concept of infinity is not an experiential nor a logical necessity. It is a mathematical necessity. This affirmation of the power of the mind, which knows itself capable of conceiving the indefinite repetition of an act, when this act is at all possible, may be pure fiction, but it is a convenient and therefore a necessary fiction. It frees us from the burden of examining in each particular case whether what we assert about the case is at all possible. It lends to our statement that appearance of generality without which there would be no science, and above all it bridges the chasm between the inescapable conception of a world which flows with the stream of time and the number concept which was born in counting the discrete. But the infinite is only one of the many bypaths through which the quest of the absolute has taken man. There are many others: simplicity, uniformity, homogeneity, regularity, causality, and other manifestations of this mathematical intuition. For it is mathematical intuition that urges the mind on to follow the mirage of the absolute and so enriches the intellectual heritage of the race. But when further pursuit of the mirage would endanger this heritage, it is mathematical intuition that halts the mind in its flight, while it whispers slyly how strangely the pursued resembles the pursuer. And what is the source of this creative intuition? What is this necessity which organizes and guides human experience and shields it from the terrors of chaos? Whence came this thrust that raised the frigid, immobile, and barren rocks of logic? Quote, "The billows are whispering their eternal whispers. The winds blow on, the clouds are sailing, the stars keep twinkling indifferent and cold, and a fool waits for his answer." End quote. And the wise man? The wise man, resuming his business in life, the spinning of the fictions of today, which may be the realities of tomorrow, casts one last glance at the distant peaks, behind which is lost the origin of thought, and repeats the words of the Master, quote, "Though the source be obscure, still the stream flows on." The end.